This is problem set number 4, problem 3. An ice-making machine operates on a Carnot cycle. It takes heat from water at 0 degrees Celsius and rejects heat to a room at 24 degrees Celsius. Suppose that 85 kilograms of water at 0 degrees Celsius are converted to ice at 0 degrees Celsius. Part A, how much heat is discharged into the room, and part B, how much energy must be supplied to the device. Okay, so I'm gonna use my energy transfer diagram that I've drawn out here, and I'm going to fill it out with the information that I know. And that will allow me to understand the problem that I'm dealing with better, right? Okay, so I have an ice-making machine, so my system is an ice-making machine, right? And it takes heat from water at 0 degrees Celsius. So my TC, it takes heat from a cold reservoir and transfers it to the system, or the ice-making machine, and that is my QC, okay? That's a heat transfer from the cold reservoir. And I know that it was given that TC, the temperature from the water and the cold reservoir, is at 0 degrees Celsius, so I'll write that down. Given my TC, my cold temperature, is equal to 0 degrees Celsius, okay? And it rejects heat to a room at 24 degrees Celsius. So the system rejects heat into the heat reservoir, or the room, at 24 degrees Celsius. So that is my QH. Okay. Actually, I'll try to write it within here. So QH. Okay. So I also know that the temperature, or the hot temperature in the heat reservoir, TH, is 24 degrees Celsius. And it rejects the heat to a room at 24 degrees Celsius. Okay. Obviously, it's an ice-making machine. Some sort of work needs to enter my system in order to make the ice. So, to complete my energy transfer diagram, I'm just gonna close this out, right? And here, work enters my system. So work is going to enter the system, and that is going to be work in. Okay. Okay. So now I have an idea of what I'm dealing with. I have my system here in yellow, right? That boundary. I transfer heat. I take heat from a cold reservoir and bring it into my system, and also use supply work into my system. Work is done on my system. And as a result, I reject a heat into a heat reservoir, which the temperature there is 24 degrees Celsius, okay? All right. Oh, and I'm also given that I'm dealing with a mass, so 85 kilograms of mass at 0 degrees Celsius is converted to ice at also 0 degrees Celsius. So I'll just write that down. So I have my givens. 85.0 kilograms. Okay. Okay. So part A, how much heat is discharged into the room? So part A, I'm looking for QH, right? how much heat am I removing from my system and bringing into the room? Okay. How could I do that? Well, we'd have to go back to what we learned in chapter 17, section 6, calorimetry and phase changes, so that we could calculate the heat transfer necessary to change phase, right? Because we are changing phase. We have 0 degrees Celsius of water, 85 kilograms of water at 0 degrees Celsius, and we're converting it to ice, also in the same temperature of 0 degrees Celsius. Okay? I'm going to make a little diagram of that, right? Okay. And this is heat added. This is going back to chapter 17. Okay. So heat added is this axis, and this axis is temperature, T. Okay. And this is for water. So here we have the solid phase. Here we have the liquid phase. And here we have steam or gas phase, right? And then this line right here, that will be my melting point. And this will be my boiling point. Okay? We know that the melting point for water so this right here, the melting point, that would be 0 degrees Celsius, right? Which is what we're given in this problem. We have 85 kilograms of water at 0 degrees Celsius, and we are converting it to ice also at 0 degrees Celsius. Okay? Okay, so if you guys recall, in chapter 17, section 6, to calculate the heat transfer necessary, right, we're going to be dealing with two things. So the first one is the heat transfer that is necessary to change temperature within the same phase. So that would be mass of material I times specific heat of material I times final temperature minus initial temperature, right? And then the other thing that the summation needs is we have plus or minus mass times the latent heat of fusion for material I, or mass times the latent heat of vaporization for material I, right? And again, in this problem, we are just dealing with 85 kilograms of water at 0 degrees Celsius converted to ice at 0 degrees Celsius. So again, this guy right here, this is heat transfer necessary to change temperature within the same phase. And these guys deals with the heat transfer necessary to change phase, right? To change phase. Okay, so clearly the problem states we're dealing with 85 kilograms of water at 0 degrees Celsius converted to ice at also 0 degrees Celsius. So because there's no temperature change in the ice, we don't need to worry about this part of heat transfer, the part that's necessary to change temperature within the same phase. We don't change temperature. We have water at 0 degrees Celsius. That's the start, and the final is ice also at 0 degrees Celsius. So all we really have is a change of phase, right? So we are just here at this melting point right here, that horizontal line, 0 degrees Celsius. Okay? So then I could say that the heat transfer necessary to change phase for that problem of having 85 kilograms of water at 0 degrees Celsius and turning it into ice at also 0 degrees Celsius would be equal to, it would be minus, right? Because we have plus or minus here. Obviously, we would use the latent heat of fusion, right? This guy. We would use this because we're going from solid to liquid. Or sorry, liquid to solid, right? So anything liquid to solid or solid to liquid, we use this formula, the top formula with latent heat of fusion. And anything dealing with liquid to gas or gas to liquid, we would use the latent heat of vaporization. So I'm going to use this guy since we're going from water to ice or liquid to solid. Okay, so now I have to choose, is it a positive or negative to begin? Well, I'm going to say, because we're going from water to ice, right? We have to, we're going down in temperature, so we would have to lose, the system would have to lose heat. You would have to transfer heat out of the system, right? So because we're transferring heat out of the system, I would use negative. So equals negative, Q is equal to negative mass that was given to us, right? That's 85. So whatever the mass is, times latent heat of fusion of water, right? That's what I want to use. Again, so that was plus or minus, and I explained why, since we're going from 0 degrees Celsius of water to 0 degrees Celsius of ice, we would use negative, okay? Because we're, heat is going to leave our system. We're going to go down in temperature, so we need to lose heat. Or we're going from liquid to solid, right? And mass, again, is 85 kilograms. And the latent heat of fusion for water is 3.34 times 10 to the 5th joules per kilogram. Okay, and I got this value for the latent heat of fusion for water on Google. So on a test, it will likely be provided to you. Okay, so I'll just plug that in my calculator, and I would find that my Q, or the heat transfer that's necessary for me to go from 0 degrees Celsius of water to 0 degrees Celsius of ice, is equal to negative 28,390,000 joules. Okay? Okay. And so recall that in chapter 20, that unlike chapter 19, where we had Q as positive or negative, this time for our QH and our QC in chapter 20, okay? So I'll call this side note 1, side note 2. In chapter 20, QH and QC are always positive, okay? So the heat transfer from the cold reservoir and the heat transfer from the heat reservoir, these are all positive. QC and QH are always positive in our case. So even though my Q is minus 28,390,000 joules, I'm going to say that my QC is equal to 28,390 or 28,390,000 joules, okay? All right, so this is, again, I'll just clarify, this is the heat transferred from the cold reservoir to the system. In this case, that's a refrigerator. Okay? And to make it clear, in this energy transfer diagram, I'm talking about this. Okay, that's the value for QC, 28,390,000 joules. All right, but what I'm not looking for QC, right? What I'm looking for in part A is actually this guy, QH. So I'm one step closer to finding my QH, but we just needed to find the QC to begin. Okay, and I'll add another side note number 3 so that this is what will help me find QH, right? So for any heat engine, my efficiency is equal to 1 minus QC over QH, right? This is from chapter 20, section 2, heat engines. And in that section, we learned that QC and QH are always positive, okay? But for a Carnot heat engine, okay, so for a Carnot heat engine, so the Carnot efficiency is equal to 1 minus cold temperature divided by hot temperature. Okay? So looking at this formula and this formula for efficiency and Carnot efficiency, right? We find that there's a property of this Carnot cycle. So therefore, a property of the Carnot cycle is that QC over QH is equal to TC over TH, right? And we can see that here. QC over QH is equal to TC over TH, right? Okay, so in a Carnot cycle, the efficiency only depends on the ratio of the absolute temperatures, right? Okay. So now using this property of the Carnot cycle, I could actually find my QH, right? Because I know my TC, I know my TH, and I know my QC, okay? So, I will use this information here. So the property of Carnot cycle is that QC over QH is equal to cold temperature over hot temperature. All right? And again, I know my value for cold heat transfer. I know my value for my temperature, my cold temperature, and I know the value for my hot temperature. So I could find the value for my hot heat transfer, right? So using this, I would find that QH is equal to cold heat transfer multiplied by hot temperature divided by cold temperature. So I'll just plug in my values. One thing to note is that the units for temperature here, I can't use Celsius. I have to convert this to Kelvin first, okay? So I'm going to do that quickly, and then I'm going to plug this back in and solve for QH. I think at this point we already know how to convert Celsius to Kelvin, but if we don't, or if we forgot, then we have a certain temperature. We have a certain temperature in degrees Kelvin, okay? And to convert that to in degrees Celsius, and to convert that to Kelvin, we would just add plus 273 to that value of degrees Celsius, and we would get our answer, or our temperature in Kelvin. Okay, so for my cold temperature, 0 plus 273, that's just 273 Kelvin. And 24 plus 273, that's just 297 Kelvin. Okay. All right, so now I'm going to plug it in. My value for QC is equal to 28,390,000 joules. My value for my hot temperature is 297 Kelvin, right? Or 24 degrees Celsius, but I need to use Kelvin. And then I divide that by my cold temperature, which is 0 degrees Celsius, and that's 273 Kelvin. All right, so I plug that in. My units cancel out with Kelvin, so I'm left with joules. And my final answer for part A is that my hot heat transfer is equal to 30,885,824.18 joules. All right, and that is my answer for part A. Okay, so that's the answer to part A. So that was the amount of heat discharged into the room. Okay? 30,885,824.18 joules. Or that was the value for this guy, QH. The heat leaving the system and entering the heat reservoir. All right. So now let's move on to part B. How much energy must be supplied to the device? Okay, so essentially what we're looking for is this work in that needs to be supplied to the device. Okay. Okay, so part B, we are looking for work in. Okay. So in order to find this, I'm going to use my first law of thermodynamics. So first law, which is change in thermal energy is equal to the net heat transferred into the system minus the work done by the system. Okay? Okay, so I'm just going to clarify this. So this is the change in thermal energy, right? Of the system. Or in other words, the change in temperature of the system or change in temperature of the refrigerator. This is our total or net heat transferred. So net, that just means total, right? Total heat transferred into the system. And this is work done by the system. Okay. So right away, what could I cancel out? There's no change in temperature in the system, right? The refrigerator doesn't change temperatures. So if there's no change in temperature of the system, I could say this is cancel that out to 0 because the refrigerator stays the same temperature. So I could rewrite this as this becomes therefore work done by the system is equal to the total heat transferred into the system, right? Well, let's look at the energy transfer diagram to find out what is the net or total heat transferred into the system. Okay? So looking at this guy, the energy transfer diagram, I could see that I add QC into my system, right? Because it goes from the cold reservoir into the system. So I have net Q is equal to positive QC because that's adding QC into the system. And I subtract QH out of the system, right? So that is my total Q. All right, so I'll rewrite that as the net heat Q is equal to, I'll rewrite that in blue so it's kind of clear. So Q, which is the total heat transferred into the system, okay, is equal to, according to our energy transfer diagram, is equal to positive QC because it enters the system from the cold reservoir minus QH because it leaves the system and enters the heat reservoir. Okay? So is equal to QC minus QH. Okay? And this is, again, based on the energy transfer diagram. That's why it's nice to draw an energy transfer diagram like we did in the beginning because it allows us to understand our problem much better, okay? So now my net Q is actually equal to QC minus QH, okay? And I know what QH is. I solved for it in part A, right here. I also know what QC is. I also solved for it in part A in order to find my QH. And I'm just going to plug those values in. Okay. I'm going to make this a little smaller so I could have more space. All right, so QC is equal to 28,390,000 joules. And I subtract that by 30,885,824.18 joules. Okay? And I would be left with negative 2,495,824 joules. More or less. I'll confirm that on the calculator. Sorry. 24.18. I'm just plugging it in my calculator, 1 second. Okay, so 24.18 joules. All right, so that would be my answer for work done by the system, okay? But is it asking us for the work done by the system? It's asking us how much energy must be supplied into the device. Anyways, so this is the work done, again. Work done by the system. Right? And I could see here I have a negative value. Right? It's negative. So that means that work was not done by the system, rather work was done on the system, which makes sense. As we see here, work enters our system. So work doesn't leave our system. That's why it's negative. Okay? So we've got a negative value. So therefore, work is done on the system and not by the system. So the answer for part B, how much energy must be supplied to the device? So 2,495,824.18 joules is supplied to the device or the system, right? And that is our final answer for part B. Okay. Hopefully that was not, I didn't go too fast and didn't skip steps. I tried to be as detailed as possible. It's probably a bit long of a video now, so let me know if you have any questions.